Okay, good afternoon again, everyone. So we will continue today with the remainder of the lecture, right? And when I finish the lecture today, we look at some problems based on what we did last day, right? Now, we don't have much again in terms of the lecture to do, right? We're looking at the initial and final value theorems today. Hopefully by the next session, we'll be able to look at problems involving initial and final value theorem. Right, so I'm going to put up the screen here. Right. Okay, this is where we stopped last day with the pole zero plot. Right. So initial and final value theorems. The following example illustrates the evaluation of a limit of the form px over qx, limit as x approaches infinity, where x is a real variable and px, qx are both polynomials in the variable x. Right, so this is fairly straightforward. Evaluate the following limits. Right, so you have a polynomial on top, a polynomial below. Right, you have a quotient of polynomials and you have a limit here approaching infinity. Right, so you have three cases here. Right, in all three cases, we first divide both the numerator and denominator by the highest power of x, right? That occurs in the denominator. So if you look at the first instant here, the highest power in the denominator is x cubed, right? So which means every term in the numerator must be divided by x cubed, and every term in the denominator must also be divided by x cubed. Similarly, the highest power in the denominator is x cubed in the second case. So you divide each value, both numerator and denominator, by x cubed, right? And the third instant here, the highest power in the denominator is x to the power 4, right? So you do likewise here in the last instant here, right? So let's look at case A, right? So here you divide each term by x cubed. So in the first value in the numerator, you'll get 1 over x, followed by 2 over x cubed. The first value in the denominator, you'll get 1. Then the second value, 1 over x, and the third value, 1 over x cubed, right? And if you take the limit now as x approaches infinity, right? So you have a fraction here, and x approaching infinity, so x getting bigger and bigger, right? So what happening here, this fraction will get smaller and smaller eventually until it approaches 0. The same will happen with the other value in the numerator and the two values in the denominator after 1. So you'll get 0 plus 0 over 1 plus 0 minus 0. So that is just 0 over 1, which is 0. Case B. So you have to divide top and bottom by x cubed, right? So you have x cubed divided by x cubed, which is 1. 5x divided by x cubed, which is 5 over x squared. 2x cubed divided by x cubed, which is 2. Minus x squared divided by x cubed, which is 1 over x. And then plus 4 divided by x cubed. So this term here will approach 0 as x approaches infinity. This term here as well, and this term here as well. So you'll just get 1 plus 0 over 2 minus 0 plus 0, which is a half. Right? And then in the third case here, in C, you divide the top and bottom, right? Each term in the top and bottom by the highest power in the denominator, which is x to the power 4. So x to the power 5 divided by x to the power 4 will be x. X cubed divided by x to the power 4 is 1 over x. X divided by x to the power 4 is 1 over x cubed. X to the power 4 divided by itself is 1. X squared divided by x to the power 4 is 1 over x squared. 1 divided by x to the power 4 is 1 over x to the power 4, right? So what would happen here? This term here, since x is in the denominator, similarly with this here, this one at the bottom here, and this one, all those will approach 0, right? But this term here, x, if this is approaching infinity, it means that this will approach infinity, right? So you'll get infinity plus 0 over 1 minus 0 minus, 1 minus 0 plus 0, which is infinity, right? So that is the evaluation of the limits in each case here. The following results is used in the proof of the initial and final value theorems, right? Theorems, page 291. So this theorem tells us that ys is the Laplace of yt, where yt is a piecewise continuous function of exponential order. Then the limit of s approaching infinity, ys is equal to 0, right? Remember, in order for a function to undergo a Laplace transform, it must be continuous, it must be piecewise continuous, and it must be of exponential order, right? Which was stated at the beginning of the program, where the limit as s approaches infinity has to be taken in such a way that the real value of s must approach infinity, right? So this here is a sketch of the proof, right? Which is not really required. You don't need to show this then, but I'll still go through it for your benefit, right? So if you take the left-hand side here, right? You have the limit of s approaching infinity, ys, the absolute value of ys. Well, we know that ys is defined to be the integral between infinity and 0, e to the minus st, yt dt. So therefore, you will be taking the absolute value of this on the right, and you're taking the limit as s approaches infinity, right? And then we know from the triangular inequality that the mod of our integral is less than or equal to the integral of the mod, right? So which means if you take the limit of s approaching infinity here, right? The limit or the integral between infinity and 0, and you take the mod of e to the minus st dt, this value here will actually be greater than or equal to this value here, right? And then we could break up this here into the real and imaginary parts, right? So you have y to the minus st, right, is e to the minus sigma t minus j omega t, right? So that is where you have s is sigma plus j omega, right? So you have here now, this will be equal to the limit as s approaches infinity, the integral between infinity and 0, e to the minus sigma t, right? Because you remember we taking we only focusing on the real value of s here. So it take the limit is taken in such a way where the real s approaching infinity. So therefore this part here just vanishes then, right? So you have the integral e to the minus sigma t, and then you take the absolute value of yt, right? And you know, if this is yt is of exponential order, then by definition, this is less than or equal to a e to the bt. So the exponential order here we're talking about is this b here, right? So if this here is the function is of exponential order, then you have to be able to find a constant here, a, and then this value here, b, is the order that will make it be of exponential order. So which means this stuff here is less than or equal to the limit of s approaching infinity, the integral of e to the minus sigma t between infinity and 0. And you replace your absolute value of yt by e to the bt. And this fact here you're using because it's of exponential order. Right? And now the a here has nothing to do with the integral. Right? The integral here is with respect to t. So you could take the a on the outside of the integral. You're taking the limit of s approaching infinity. And then you're combining the e to the minus sigma t, e to the bt. So you get e to the b minus sigma t. Right? And then you take the limit here, as s approaches infinity, a, and this part here, you change the upper limit here, infinity here to r, and you take the limit of r approaching infinity. The integral between r and 0, e to the b minus sigma t dt. And then this here, the integral, if you integrate this here, you'll get e to the b minus r over b minus r. And you could take the b minus sigma, and you could take the b minus sigma on the outside here because that is a constant under the a. And then you evaluate here the limit of e to the b minus sigma r. And then if you put in 0 here, you get minus 1. Right? And of course, this here, we are assuming that sigma is greater, much greater. The double arrow here means much greater than b. So if sigma is much greater than b, it means that this value on top here will be negative, right? So you'll have a negative value on top here. So e to some negative value. So once that approaches a negative value, an exponential to a negative power means that this here will approach 0, right? So you have the limit of s approaching infinity, a over b minus sigma. In brackets here, this term here will be 0, and then minus 1, right? So then the minus 1 here now, you'll get minus a over b minus sigma, which is the same as a over sigma minus b. You swing around the terms in the denominator. And this here as s approaches infinity, you remember s approaching infinity along the real axis. So real s, right, approaches infinity. So in terms of what term here represents the real s, right? Sigma here will be that number, right? Sigma approaches infinity, right? So if sigma approaches infinity, therefore the denominator here will approach infinity. So you'll have this whole value here will approach 0, right? And look, it's written here. So therefore, if this is 0 and we go back up to the top here, it means that the limit of s approaching infinity, the absolute value of ys will be 0, right? So it implies that the limit of s approaching infinity, ys is just 0 as required. Any questions on that? It's supposed to be an equal here, right? Okay, digression. Every rational fraction or every rational function Ps over Qs on the complex S plane may be extended to a continuous function on the Riemann sphere. In particular, Ps over Qs, right, is such that C P prime approaches C P prime is continuous and S equal infinity. At S equal infinity, and therefore the limit of PS as S approaches infinity, the limit of PS over QS may be calculated for any path S approaching infinity. In particular, we may choose S approaching infinity along the real axis as we did in the previous case. Note that the above argument is false if PS over QS is not rational. For example, right? So you have the limit Z approaching infinity, Z over Z conjugate, right? So if you're writing Z over Z conjugate, Z will be written in complex form as R e to the I theta, and Z conjugate will be R e to the minus I theta, right? So if you'll notice here, the R's will cancel each other. You'll get e to the I theta plus I theta, which is e to the 2I theta. And then you're focusing along the real axis. So you have e to the 2 theta. Now this here could also be written, right? R e to the I theta could be written as R into cos theta plus I sine theta. And R e to the minus I theta could be written as cos theta minus I sine theta. Right? So if you break up this here, right, then it will be 1 along the real axis. Because what will happen here? The real axis, this part here will cancel. The real axis going to have this part here. So it will be R cos theta over R cos theta, which is 1, right? And if you're focusing along the imaginary axis, then the cos part will vanish, right? So therefore, this part here will vanish. So you'll get R sine I sine theta over R minus I sine theta. So everything will cancel, so you end up with minus 1. Right? So you see how, right? So I just do that there to show you. Right? So the limit of this here, Z over Z conjugate, is equal to 1 along the real axis and minus 1 along the imaginary axis. Let yt equal, so let's look at an example of this now. Let yt equal t squared plus e to the t. Show that ys as s approaches infinity is equal to 0, where ys is the Laplace of yt. So if we take the Laplace yt, we take the Laplace t squared plus e to the t. The Laplace t squared is 2 factorial over s cubed plus 1 over s minus 1. And we know 2 factorial is just 2. So now the limit of s approaching infinity ys will be the limit of 2 over s cubed plus 1 over s minus 1. So therefore we break up this here using the linearity. So the limit of s approaching infinity 2 over s cubed plus the limit of s approaching infinity 1 over s minus 1. Right? And then, of course, this one here, the limit of 2 over s cubed as s approaching infinity here will be 0. And then here now, you're divided by the highest power s, so you'll have 1 over s in the numerator. 1 here minus 1 over s. So on top here now, this could be 0, and this will be 0. So you get 0 over 1 minus 0, which is 0. 0 plus 0 is 0. Suppose that a Laplace transform is known, but its inverse Laplace transform is unknown. Then we may use the following initial value theorem to determine the initial value without actually calculating the inverse transform. So this is the benefit of using the initial value theorem. You could find your initial condition without actually calculating the inverse transform, right? And then you could verify, you could calculate the inverse transform and verify it for yourself, you know, just as a check, but it's not necessary. Theorem, initial value theorem. Let yt be continuous and of exponential order, and let y, the derivative of yt be piecewise continuous on every finite interval and of exponential order. Then the initial condition y naught is equal to the limit at s approaching infinity, sys. So s times the Laplace transform. We can remember ys is the Laplace transform of yt, ft rather, right? I said ft, sorry, is yt, right? Where ys is equal to the Laplace transform of yt, right? So we could sketch this proof here. Remember, the Laplace transform of the first derivative of yt is sys minus y naught, right? So from the previous result, we know that the limit of s approaching infinity, the Laplace of y prime t is equal to 0. Why? Because look at what happened here. This here y naught is the limit of s approaching infinity, sys. And this here, the sys, replace that with y naught. So y naught minus y naught is 0. So that is why you get 0 here. So the limit of y prime t will be just the limit of s approaching infinity, sys minus y naught. And we already know that sys is y naught. So you have y naught minus y naught is 0. Then taking the limit of 28 as s approaching infinity gives the limit of the Laplace of y prime t is equal to the limit of s approaching infinity, sys minus y naught, right? And we know that this here is 0, so the left hand side is 0. So the limit of sys minus y0 will be the limit of s approaching infinity, sys equal y0 as required. Let ys be s over s squared plus 1. Use the initial value theorem to obtain y naught without calculating the inverse transform of yt. Calculate the inverse transform of ys and hence determine y naught. Compare this answer with your answer from part A. So you'll see that the two answers correspond then. So let's look at the first part here now. So use the initial value theorem. So this is the initial value theorem. From the initial value theorem, y naught is the limit of s approaching infinity, s ys, which is the Laplace transform of yt. And that was given to be s over s squared plus 1. So that is the limit of s approaching infinity, s by s over s squared plus 1. So that gives us s squared over s squared plus 1. And then if you take the limit here, since this is like a polynomial, then you divide the top and bottom by the highest power in the denominator, which is s squared. So you'll end up getting 1 in the numerator over 1 plus 1 over s squared. And if you take the limit here as s approaches infinity, this value here will be 0. So you'll get 1 over 1, which is 1. Right? So y naught is 1. So the initial condition here is 1. Right? So part B now suggests that you take the Laplace transform on ys to see if that really is the case, right? So we know that the Laplace transform on s over s squared plus 1 is cos t, right? So y t will be cos t. And the initial condition here, if you replace t here by 0, y 0, you'll get cos 0, which is 1. So you see how these two answers here coincide, watch it. But the benefit of finding the initial condition here without taking the inverse transform, right? You didn't have to take the inverse transform in part B. So that is convenient because sometimes you might remember how to find the inverse transform. If it's a complicated Laplace transform function you're dealing with, which agrees with the answer from part A. So the proposition here, Ogata, page 25, let the Laplace transform of yt equal to ys, where ys is ps over qs, is the ratio of two polynomials, ps, qs, if all poles of sys lie strictly in the left hand of the complex S-plane, right? Then the limit at t approaching infinity, ft exists, right? But if sys has poles on the imaginary axis or strictly in the right hand of the complex S-plane, then the function ft will contain oscillating or exponentially increasing time functions, and hence the limit at t approaching infinity, ft will not exist, right? So that is something very important, and when we're doing some of the problems, you will see what you'll see in the diagram actual representation of this. So your poles, all of them must lie in the left hand plane, right? So if I draw a little diagram here, this is the left hand plane here, right? And this here is the right hand plane. Right, so this is the right hand plane. And this on the left hand side of the imaginary axis is the left hand plane. Right? So if the poles all lie on this side here, on the left hand side, it means that the limit of the function as t approaching infinity will exist. If some poles lie on the imaginary axis and on the right hand, right, then the limit won't exist, right? So that is something important. Right, so let me just take a 2-minute break here now, right? Yeah. Yeah, hold on. Okay, so let's continue there. right? So if the poles and them lie on the left-hand side of the S-plane, it means that you'll have the limit existing. If any pole lies on the imaginary axis on the right-hand side, then you don't have the limit existing. And then that could tie into what you call stability, right? And then we have the concept of stability, we have unstable, and we have marginally stable. And then I'll talk about that when we go through some of the questions. So example, let ys equal 1 over s squared plus 1. And consider sys is equal to s over, right? Because you have to multiply by s over s squared plus 1, right? So in order for us to determine the poles here, right? The poles are the zeros in the denominator, right? So if you notice here, s squared plus 1 must be equal to 0. So that is how you work out your poles. So if s squared plus 1 is equal to 0, then s squared must be minus 1. So this implies that s must be plus or minus the square root of minus 1. So plus or minus the square root of minus 1 is really plus or minus j. So these poles here are complex, right? And anytime you have complex poles, you remember the complex poles on them are current conjugate pairs, right? So you have s plus j, right? So this is the case here when the pole is minus j, and this case here is when the pole is plus j, because minus j plus j is 0, plus j minus j is 0. And these two poles will lie exactly on the imaginary axis. Because if I draw a little diagram here, this is real S, and this is IMS, right? And this will be J here, and this will be minus J below here, right? And remember, normally we will draw a pole as a little X. So one pole will be here, and one pole will be here, right? So based on the theory here, they say once the pole lie on the imaginary axis, right? Then the limit wouldn't exist, right? So here now, the limit at t approaching infinity, yt does not exist. This could be confirmed by recalculating yt. You're taking the Laplace transform ys, which is 1 over s squared plus 1. And we know that the Laplace transform 1 over s squared plus 1 is sine t. And then if you take this here, sine t as t approaching infinity, doesn't exist, because sine t, what you're going to have is oscillation up and down. You have an oscillation, right? Something like this. But you know what I mean? I didn't draw it too perfect there, but just as how the sine graph does go, up and down you're oscillating. And so on, right? So the limit there doesn't exist with the function sine t. So now we're looking at the final value theorem. Any questions on the initial value theorem before I continue? No questions so far? Okay. So let's look at the final value theorem now. Let yt equal ys. The Laplace transform of yt is ys, where yt is continuous and of exponential order. And where y prime t, which is the derivative of yt, is piecewise continuous on every finite interval and is of exponential order. If all poles of SYS lie strictly in the left hand of the complex S-plane, then the final value theorem of yt is given by the limit at t approaching infinity yt is the limit at s approaching 0 SYS. So that is when all the poles lie strictly in the left-hand plane. Then the limit, to calculate the limit of the function yt as t approaches infinity, you take the limit at s approaching 0, s time your Laplace transform of yt, which is ys. And the proof of that is the limit of the derivative of yt, or the Laplace transform of the derivative of yt is sys minus y naught. And we know that the left-hand side here, by definition, is the integral between infinity and 0 e to the minus sty prime t dt, which is sys minus y naught. And if we take the limit as s approaches in 0 on both sides here, we'll get s approaching 0 on the left-hand side, and the limit of s approaching 0 sys minus y naught on the right-hand side. And then this will imply that you put the limit on the inside here within the integral, s approaching 0 e to the minus sty prime t. And then the right-hand side here, the limit of s approaching 0 sys minus y naught. And of course here, if this is negative and s approaches 0 here, right? Anything to the 0 is 1, so that will just be integral between infinity and 0 y prime t is equal, dt is equal to the limit of s approaching 0 sys minus y naught. And this here now, the integral between infinity and 0 y prime t, you could take that as the limit here at t approaching infinity yt minus y naught, which is the limit of s approaching 0 sys minus y naught. And then the minus y naught drops off on both sides, right? So you'll end up getting the limit at t approaching infinity yt is equal to the limit at s approaching 0 sys, which is what we require, right? Because if you integrate this here, right, you'll just get back yt. If you integrate y prime t, you'll get back yt, and then you evaluate this between infinity and 0. So therefore, what you'll get here, you'll get the limit here at t approaching infinity yt, that is the first term, and then minus the lower limit here, which is y0, right? That is how you get this here then. So we see how the result here is obtained. So the limit at t approaching infinity yt is the limit at s approaching 0 sys. So this is the final value theorem. So the example here, ys is 1 over s into s plus 1. Determine if the poles of sys satisfy the conditions of the final value theorem. That is part A, and part B now evaluate the limit at t approaching infinity yt without calculating yt. Without calculating the inverse transform of ys. And C here, calculate yt, which is the Laplace inverse of ys, and hence determine the limit at t approaching infinity yt. compare this answer with your answer in part B, right? So remember part A now, you need to find SYS. So that will be S into 1 over S into S plus 1, which is just 1 over S plus 1. So which means SYS has a simple pole at S equal minus 1. Remember, to determine the poles, the poles are the zeros in the denominator. So S plus 1 had to be equal to 0. So S had to be minus 1. So minus 1 is a pole, a simple pole, because the order of the pole is 1. And where does minus 1 lie? If we draw a little diagram here, minus 1 will lie here, somewhere here, right? So you notice that is in the left-hand plane, which is on this side, right? So it lies strictly in the left-hand side of the complex S-plane. Hence, the pole of SY satisfies the condition of the final value theorem. So if you want to find the limit at t approaching infinity, yt, you take the limit at s approaching 0, SYS, which we already worked out to be 1 over S plus 1. And then if you take S approaching 0 here, you'll get 1 over 1, which is 1. So the limit of yt is 1. Right, so let me compare that now. Let me find the inverse transform of ys. Right, so if we use partial fractions here, we realize that this is 1 over S minus 1 over S plus 1. And the inverse of 1 over S is 1. The inverse of 1 over S minus 1 is e to the minus t. So you'll get 1 minus e to the minus t. And if we take the limit here, this approaching infinity, you'll be taking 1, the limit of t approaching infinity, 1 minus e to the minus t. So e to the minus t here go approach 0. So you will just get 1 minus 0 is 1, which agrees with the answer in part B. Right? Right. So this is where we would come to a conclusion in terms of the lectures, right? So this is what you need to know, all that you need to know in order to do your exam, right? So this is, all this will come in the final exam. Right, so let me put up some questions involving what we did here. Right. Right. Poles and zeros of transfer functions. Right. So this what we doing here, these questions related to what we did last day. Right. And what we did today. We'll do some questions on that in the next session on Wednesday, right? So you have the transfer function here. Psi s is s minus 6 over s into s squared plus 4x plus 13. Find the poles and zeros and produce a plot identifying them on the S-plane. Right? Now, the difference between the poles and the zeros. The poles are the zeros in the denominator, and the zero are the zeros in the numerator, right? So S minus 6 equals 0. S, whatever value S works out to be, will be a 0, right? So you notice here S minus 6 here. For this to be 0, S had to be 6. So S equals 6 is a 0, right? Clearly, we could see one of the poles here. If S is 0 here, that is a pole. So that is a pole. To work out the other poles here now, we have to put S squared plus 4S plus 13, which is S plus 2 squared plus 9, right? And if we use the completing the square here, we will get S plus 2 squared is equal to minus 9. So we have to put this equal to 0, right? So you get S plus 2 squared is minus 9. So s plus 2 will be plus or minus the square root of minus 9, which is plus or minus 3j. And then s will be minus 2 plus or minus 3j. So you have two complex poles here, right? So you have a real pole at s equals 0 and two complex poles at s equal minus 2 plus 3j and s equal minus 2 minus 3j. So you could write the transfer function here now, phi s, right, in factored form as s minus 6 over s into s minus minus 2 plus 3j in bracket, and then s minus minus 2 minus 3j in bracket, right? So I could close off this here with another bracket. So now we want to sketch the poles and the zeros in the S-plane. So you have your plot here, your S-plane, your real S and your imaginary S. So this is how you label it. A zero is always indicated by a circle and a pole bar X. So you could what you could do, you could write a little legend here. 0 represents a 0 and X represents a pole. And you have a pole at s equals 0, so that is by the origin here. You have a 0 at 6 here, that is on the right hand plane. And then you have two complex poles, minus 2 plus 3j and minus 2 minus 3j, right? Is that all right? Everybody follow that? So I have my 3 poles here and I have my 0 here. Question number 2. Right. Consider the transfer function, right? GS is 2 into s plus 1 over s cubed plus 4s plus this is supposed to be squared, eh? Sorry about that. 4s squared plus 6s plus 4. Now this value here, this constant, we call this the gain, right? So anytime you have a value that outside multiplying by the two polynomials, basically, this is the gain of the circuit. If it's a circuit, the gain of the circuit. Determine the pole and zeros and produce a sketch indicating their position on the S-plane. So you're doing the same thing here again. So to make the numerator 0, s is minus 1. So minus 1 is a 0. To make the denominator 0, to find your poles, s cubed plus 4s squared plus 6s plus 4. Right? So this is a polynomial here of 3rd degree then. So if you want to factorize a polynomial at 3rd degree, one of the ways to do it is to find a factor, right? To look for a simple factor. So you could try 1, you could try minus 1, you could try 2, you could try minus 2. Now when I try minus 2 here, again minus 2 cubed plus 4 by minus 2 squared plus 6 by minus 2 plus 4. So I end up with minus 8 plus 16 minus 12 plus 4, which working out as 0. So if minus 2, when you plug it into the polynomial again 0, it means that s plus 2 is a factor. Right? So what I could do here, I could do long division here. I could divide the polynomial here by s plus 2. S cubed plus 4s squared plus 6s plus 4. And then s plus 2 into s cubed. Right? So s squared. And then you multiply s squared by s. You get s cubed. And you multiply the s squared by 2. You get 2s squared. Now, in order for the s cubed to cancel, this had to be minus, so therefore this had to be minus here. So you'll end up with 4s squared minus 2s squared, which is 2s squared. And then you say s into 2s squared, that will give you 2s. And then you multiply 2s by s, you get your 2s squared, and your 2s by 2, you get 4s. And then for the 2s squared to cancel with the 2s squared, this had to be negative. So therefore the other term had to be negative as well. So 6s minus 4s is 2s. S into 2s is 2. 2 by s is 2s, and 2 by 2 is 4. And that, for the 2s to cancel, this had to be negative and this had to be negative. So 4 minus 4 is 0. So your next factor will be s squared plus 2s plus 2. Right? And now from this factor, you could complete the square. This is s plus 1 squared plus 1. So s plus 1 squared is minus 1. So s plus 1 is plus or minus j. So s is plus, s is minus 1 plus or minus j. So therefore, your factors would be s minus into minus 1 plus j and s minus into minus 1 minus j. So you have two complex factors and you have a simple factor. So what you are writing here, gs, the transfer function in terms of the factors now in the denominator, s plus 1 over s plus 2, s minus minus 1 plus j, and then s minus open bracket into minus 1 minus j. So I could safely say now that the poles lie at s minus, s equal minus 2, s equal minus 1 plus j, and s equal minus 1 minus j, which are the two conjugate complex poles, right? So if I sketch the S-plane now, x minus 2 is here. So I have a x representing the pole, with 0 at minus 1, right? So that is here, a circle by minus 1, and minus 1 plus j, that will be up here, and minus 1 minus j, that will be down here, right? Right? So you notice here, all your poles lie in the left-hand plane. They didn't ask you that. So that means the limiter ft as t approaches infinity here wouldn't exist. Right? So this, sorry, it would exist. Right? If everything that lie in the right-hand side on the axis, on the imaginary axis, then it wouldn't exist. But remember, the only thing that determines existence of ft as t approaches infinity is the poles, not the zeros. So it's just the poles specifically you have to look at. Although the diagram will tell you to plot the zero, you have to plot it as well. But the poles is really the key to determine if the limit of the function ft as t approaches infinity exists or not. Okay, number 3. Sketch the pole 0 plot for the following transfer function. 100 over s plus 30. HS is 100 into s plus 1 over s plus 10 into s plus 100. The next one, 10 into s plus 10 over s squared plus 35. The 100 into s over s cubed plus 12s squared plus 21s plus 10. HS is 30 into s plus 10 over s squared plus 3s plus 50. And f, the transfer function here, 4 into s squared plus s plus 25 over s cubed plus 100s squared. Right? So we're going on and sketch the pole 0 plot for each one of these here from A to F. Right. So look at the first one here. S equal minus 30 is a pole. There are no zeros. If there are no value in the numerator, that could make the numerator 0. So you have no zeros. So look at the imaginary axis, the real axis, and the S-plane. So you have a x by minus 30 in the left-hand plane. Next one, 100 into S plus 1 over S plus 10 into S plus 100. So you have a 0 here at S equal minus 1. You have a pole at S equal minus 10 and S equal minus 100. Two simple poles, right? So X represent your pole, 0 represent your 0. You have your S-plane, imaginary axis, real axis. So look at draw the circle here by minus 1, right? I have a X here by minus 10, right? So let me assume this is minus 10 here, right? And this is minus 100 here. So you have a X here. Any questions on that so far? Okay. HS is 10 into S plus 10 over S squared plus 35. So you have a S equal to the square root of 35J is a complex pole, and S equal minus 10 is a 0. So you explain here again. Minus 10 here is your 0. And your square root of 35 is exactly on the imaginary axis, a little above 6J. The square root of 35 is about 6 point something. So, right? So this will be an example here with the limit at t approaching infinity, ft wouldn't exist because the pole here lie on the imaginary axis. Part D now, minus 100 into S over S cubed plus 12S squared plus 21S plus 10. So on top here now, if you factorize this here, the denominator, right? If you put S equal minus 1 here, you'll get this denominator to work out to 0. So it means that S plus 1 is a factor. So when I divide S cubed plus 12S squared plus 21S plus 10 by S plus 1, and I do my long division, S into S cubed is S squared, and then I multiply again minus, I get S cubed here, and I get plus S squared, and then to cancel the S cubed, I had to make this negative, so this had to be negative as well. So when I subtract, I'll get 11S squared. S into 11S squared is plus 11S. And when I multiply, I'll get 11S squared, and I'll get plus 11S. And then to cancel here, this had to be negative, and this will also have to be negative. So 21 minus 11 is 10. So S into 10S is 10, and 10 by S is 10S. And 10 by 1 is 10. And then to cancel here, this will have to be negative, and this will have to be negative. So you'll end up getting 0. Right? Now, if you notice something here, you'll end up getting S plus 1, right? And S plus 1 occurring twice, because this factor here if you factorize s squared plus 11x plus 10, you'll get s plus 1, and you'll get s plus 10. That's for this here. So from that quadratic, you'll get two simple factors. But remember, you don't have s plus 1 as a simple factor. So you have s plus 1, s plus 10, s plus 1. So you have s plus 1 squared, s plus 10. So which means s minus equal minus 1 is a double pole because the order here is 2. And s equal minus 10 is a simple pole. And then in the numerator, for that to be 0, s equals 0 is a 0. So when you're plotting that on the s-plane here, your s equals 0, your 0 here, right? So your 0 is indicated by O, and your pole by x. Right? So your 0 here by the origin, and you have a minus 1 is a pole, a double pole. So it by minus 1 here in the left hand plane, and minus 10 is another pole here. Right? And the last question in this, the last part in question 3 here, HS is 30 into s plus 10 over s squared plus 3s plus 50. Right. So s equal minus 10 is a 0. And then to find the poles now, you have to put the denominator equal to 0. And then that will factorize into minus 3 over 2 plus j, the square root of 191 over 2. And minus 3 over 2 minus j, the square root of 191 over 2. And s equal minus 10 is a 0. So you have your pole 0 plot here, right? So you have minus 191 over 2j, right? Falling somewhere between 8 and 6j. And then you have it between minus 8 and minus 6j at the bottom here, then in the imaginary axis. And then 3 minus 3 over 2 will be between minus 1 and minus 2. So this is the position of your pole here. And this is your 0 here. Right? Is that okay so far? Right. So the most complicated thing here to do is really when you get like a polynomial where you have to factorize it and find out the poles and the zeros. If it's complex and you have to do some kind of complicated simplification, but generally once you're able to find your poles and zeros, it shouldn't be difficult to plot it on the z plane, on the s plane rather, right? All right, look this one here. I didn't realize we have up to f. So you have s squared plus s plus 25 over s cubed plus 100 s squared. So you have the denominator, you can factor out the s squared here. So you have s squared into s plus 100. So s equals 0 is a double pole. S equal minus 100 is a simple pole. Right? And if you notice the numerator here, you're going to end up having complex zeros. Right? Because if you factorize s squared plus s plus 25, you'll get minus a half plus the square root of 99 over 2j. And you'll get minus a half minus the square root of 99 over 2j. So the square root of 99 over 2j lies somewhere between 6j and 4j. And then the same will exist for the minus the square root of 99 over. Right. So this is like almost 10 divided by 2 will be 5 then. So minus 5 and plus 5 somewhere around there. So this is where your 0 will lie. Minus a half between minus 1 and 0 up here and down here. And you have your poles at 0 and minus 100. Right? So here you have a pole lying on the imaginary axis. So this will tell you that the limit at t approaching infinity, ft wouldn't exist. Because for the limit to exist, all the poles must be in the left-hand plane. Okay, so let's look at question 4 now. Consider the following transfer functions. Calculate the poles and zeros of the system. Draw the pole 0 plot. Determine the stability of the system. So you have A, B, C, and D. Okay, so let's look at A. S plus 3 over S into S plus 2. So that is your transfer function there. So your poles will lie at S equals 0 and S equals minus 2. And they would be two simple poles, and S equals minus 3 is at 0. So look at my pole 0 plot there. X by the origin and X by minus 2. And 0 by minus 3. And you have your left hand plane here, right? The system is marginally stable since a pole lies on the imaginary axis. So because all the poles not on the left hand plane, you have a pole here on the imaginary axis. So we say that the system is marginally stable. So it's three concepts: marginally stable, stable, or unstable. Right? And this is a little representation of what marginally stable will be. Right? You will have an oscillation, but the amplitude of the oscillation will remain constant. You understand? So you notice the height here is the same as you go along. So this here, the limit wouldn't exist. Right? In marginal stability, you have oscillation up and down with the same amplitude. So you do have no limit being approached. Part B. S over S plus 1 into S plus 2 into S plus 3. So you have a pole at minus 1, a pole at minus 2, and a pole at minus 3. Three simple poles. And you have a 0 at S equals 0. So what's going on here? You have your 0 on the imaginary axis. The 0 has nothing to do with the stability of the system. It's just the poles you're looking at. All the poles lie in the left-hand plane, right? So since that is the case, all the poles lie in the left-hand plane or the S plane, the system is stable. And this is a little diagram here showing you will have oscillation, and then what will happen here? It will fizzle out. So fizzling out means that this system here will approach a limit then. So this is the diagram here showing stability, and therefore the limit as t approaches infinity, ft will exist. Because the oscillation comes to, the height of the oscillation gets smaller and smaller and fizzles out. So which means it would approach a limit. So this is marginally stable. This is stable, right? Case 3 here, watch out it here. S plus 3 squared, S into S squared plus 10. S equals 0 is a simple pole. And S equal plus or minus the square root of 10j would be two complex poles, right? So S equal minus 3 is a 0. So you have your 0 here, minus 3 on the left-hand side. You have your 3 poles on the imaginary axis. So all your poles lying on the imaginary axis, therefore the system is marginally stable. So this one, the diagram for it will be similar to this one here. You have repeated oscillation, amplitude remaining constant. The final example now. GS is equal to S into S plus 1 over S minus 1 into S minus 2 into S squared minus 7S plus 12. Right? So what I did here, factorize the denominator into S minus 1, S minus 2, S minus 3, S minus 4. So therefore, S equal 1, 2, 3, and 4 are simple poles. S equals 0 is a 0 of order 2, and S equal minus 1 is also a 0. Right? So watch where your poles are them lying on the right hand side of the S plane. Right? So you have a pole here by 1, 2, 3, and 4. You have a 0 by the origin, and you have a 0 here by minus 1. So all the poles lie in the right-hand plane of the S plane. Therefore, the system is unstable. So therefore, the limit here, as t approaching infinity, ft doesn't exist. So this is a diagram here illustrating an unstable system. So watch what happening. You have the amplitude here getting higher and higher. The oscillation getting larger and larger. It will keep getting larger and larger and going on and on. So which means the limit, it would not approach a limit. Right? So these are the 3 instances here describing a system. Right? Stable, unstable, marginally stable. Remember, the only time the limit of the function will exist is when you have stability. And that is when all the poles lie in the left-hand plane. Right. Any questions on that? No questions? I hope you're happy with that explanation and all those examples, right? I think it should be clear to you now how to go about doing this. Now, the next day when we meet, we'll go through some of the examples involving the initial and final value theorem application. And then if time allows, we will look at maybe some of the questions from past exams, final exams. Remember, the next day we meet is Wednesday. So that would be the last day, because Friday, the time on Friday is really the time to do your midterm exam, where you would log in between 1 and 3, right? So that exam, you will see that exam in eClassroom sometime early next week when you're going to eClassroom. When I say eClassroom, I mean my e-learning, right? You would see it, but you wouldn't be able to do it until Friday at 1 p.m. Right? Any questions on what we did so far? All right. Well, if there are no questions, then we could stop here. Right? So take care. I'll see you again next Wednesday. Okay.